Hello, calculus people. First and foremost, I want to apologize to those of you that may have tried to view the video from Wednesday. So I think what happened on Wednesday was I pressed the pause recording by accident. So you had a link to an 8-second video, which was super frustrating. But what I'll try to do quickly to start here is to just kind of quickly review the big topics that we saw on Wednesday. And what I'll do is I'll print this out as a PDF document and upload these notes for you guys as well. So you can just kind of grab them right from the Moodle page. So on Wednesday, we had kind of discussed, you know, if you're given a rational function where you have a polynomial divided by a polynomial, and you know that the degree of the, numerator is smaller than the degree of the denominator, then you can go through this procedure of partial fraction decomposition. So the idea here is if you have a numerator that has an equal or larger degree, you probably are going to try to substitute, or you're probably going to try to do long division first. And then after you kind of finish that procedure, then you can start working on the decomposition. And we decompose in just a very specific way. So essentially we try to take that denominator, try to factor it into linear factors as much as possible. Sometimes you end up getting quadratic factors that you can't factor any further. These are known as irreducible quadratic factors. So these are things that look like x squared plus a. Those things can't be factored any further. Or they could be of the form ax squared plus bx plus c, where the when we go to apply the quadratic formula, the b squared minus 4ac is less than 0. So you get a negative underneath the square root. So it's possible for them to come in those two different forms. And then essentially what we want to do is we want to set up the original fraction as a sum of these decomposed fractions. And we do it in a very specific way. So every linear factor gets a single constant in the numerator. Every quadratic factor that's irreducible gets an ax plus b, or a constant times x plus b. It gets a linear factor in the numerator. And then if you have any repeated factors inside of the denominator, you need to make sure to have increasing powers inside of your decomposition. So we looked at a couple examples here, and you can kind of take a rough look through these examples, but let's take number 2 and 3 as just kind of quick refreshers. So number 2, I fully factored the denominator. I have an x plus 1 to the power of 3. So I need 3 copies of this inside my decomposition. I need an x plus 1 to the single power, an x plus 1 to the second power, and an x plus 1 to the third power. Each of the numerators gets a constant number because this is a linear factor. And then moving over to the next one, we have an x squared plus 4 as our next factor. So that, an x plus 4 as our next factor, but notice that it has 2 copies. It's x squared plus 4 all squared. So I need, over on the right-hand side of the equation, an x plus 4 single and an x plus 4 to the secondary power. And because this is an irreducible quadratic, each of those numerators gets a linear kind of thing. So that's where the dx plus e and the fx plus g comes from. So that's kind of the lowdown of just setting up the decomposition. A couple helpful formulas. It might be helpful just to have the sum and difference of cubes formulas handy in case you need to factor a cubic kind of thing. And then we worked on a couple full examples. I'll let you guys kind of go back and take a look at the full examples. And the goal today is we're going to work through just a couple more full examples. So you have a few more examples in your notes. So here is the next full example I would like to cover. It is the integral. We have x4 over x squared plus 1 squared. Okay, so taking a look at this particular integral, we do want to be A little careful here because I do notice that in the denominator we have an x squared squared. So if I was to expand this denominator out, I'm going to notice that I do need to go through the long division procedure in order to simplify this a little bit first. Okay, so that's what I'm going to be doing in green here. I'm going to go through the long division procedure to try to simplify this. And we're going to take x to the 4, and we're going to divide that by x to the 4 plus 2x squared plus 1. Okay, so I'm going to set up, I guess, a bunch of placeholders here. And then notice that I really just need one copy of the thing that I'm working with. So 1 times x to the 4, 1 times 2x squared, and then 1 times 1. And then we're going to be going through a subtraction step here at the bottom. So we do get 0 here. We get 0 take away 2, so negative 2x squared, and 0 take away 1. Okay, so the long division procedure basically says we can take this integral that we have up top, and we can rewrite it as 1 whole unit plus this remaining unit, which is negative 2x squared minus 1 over top of this thing. Okay, so I'm maybe just going to take a moment to, let's see, just kind of rewrite this second fraction a little bit. So we should get integral of 1 dx, and I'm going to maybe factor out that minus sign as well. So let's factor out the minus sign. That'll give us 2x squared plus 1. And what do we get down here? 4x, that's not good, so let's write x squared plus 1. Let's kind of refactor that denominator into its perfect square as well. Okay, so this is a simpler looking integral than what we had started with. We can go ahead, we can integrate this first term. That's just going to give us x. Okay, so our real goal is to now kind of figure out how to work with this secondary fraction. So I am thinking that it doesn't look like a substitution is going to be helpful. So I think we're going to try to decompose this into the following. It would be helpful if I could decompose this into something over x squared plus 1. Is this going to work? Plus something, and these are going to be ax. I think this will be helpful. Let's see how this works. So this is technically the partial fraction decomposition form. It says, because I have an irreducible quadratic in the denominator, let's consider both powers in the decomposed form. And we're trying to kind of simplify this numerator a little bit. So the numerator currently has a 2x squared. Inside my decomposition, we want linear kinds of things. And that's going to make it hopefully a little bit easier for us to integrate overall. So in green, I'm going to try to set this up. So we have the original fraction. Maybe I'll just move this over because we might need a little bit more room. And this should be equal to ax plus b over some stuff, plus cx plus d over some stuff. Now, this already has the common denominator, so I don't really need to do anything to that one. But what I do need to do to this first one is just multiply by x squared plus 1. Okay, so I'm going to multiply both the numerator and denominator by x squared plus 1, and we're going to get something that looks like this. And so now that we found that common denominator, we know that really it's just the numerators that we're curious about. So 2x squared plus 1, we want that to be equal to ax plus b times x squared plus 1 plus cx plus d. And our goal is to try to find the numbers a, b, c, and d. And then hopefully when we do that, that's going to give us a path to move forward. Now, this could potentially kind of not be nice for substitution. So this equation has to work for every x value. In particular, x is equal to 0, for example, but I'm trying to look for an x value where I can kind of cancel out some stuff, but it doesn't look like there's an easy x value to choose to make that work. So what I'm going to decide to do here over on the right-hand side is just expand this out, and then maybe some of the coefficients, the values, are going to kind of reveal themselves to us here. So multiplying out this first bit, we get ax cubed plus ax plus bx squared plus b plus cx plus d. Okay, so right away, I pretty much know that a is equal to 0. And I know that a is equal to 0 because right here we have an a cubed, but there's no a cubes over on the left-hand side. There's no x cubes. So I have a times x cubed. There's no x cubes over here, so it makes sense for a to be equal to 0. Now, if a is equal to 0, can we kind of zero in, no pun intended, on another value, b, c, or d? So if a was 0, we have bx squared plus cx plus b plus d. Now, it also kind of looks like c should be 0. Right, so let's get rid of c, right? There are no x terms over on the left-hand side. So now we have 2x squared plus 1 is equal to the following. And next we're going to take a look at the x squared terms. So it looks like we have 2x squared terms. So my guess here is that b must be equal to 2, just kind of comparing these things. And if b was equal to 2, we'd have something like this. We'd have 2x squareds plus 2 plus d. All right. So that's good. Those two things, that works. Once we get rid of those two things, now we have the capacity to actually solve for d. d is equal to -1. So that's our final number that we're looking for. So I'm going to go back. I'm going to copy and paste our partial fraction bit down at the bottom. And then we're going to kind of analyze this in hopes that we can move forward with this question. Okay. So what did we find? We found that, I believe, a was equal to 0. A and c were 0. B was equal to 2. C was 0, and D was equal to -1. So I'm going to put, oops. Okay, so hopefully, I think I can kind of see how we need to tackle this first integral. The first integral seems like it kind of makes sense to me. So let's go, let's factor that 2 out. And now we have an arctan integral. And then distributing that minus sign through, we're going to get a plus integral of 1 over this stuff. So this second integral, this one bugs me a little bit more. This one's definitely arctan. This one's a little curious. What if we, well, what do I know? I know that, say, tan squared plus 1 is equal to secant squared. So I could maybe switch this out for, like, secant. Can Can I do that? Can I get secant squared? Yeah, and so I think the try here is to maybe try a trig substitution and see what happens. So let's try making x equal to tan theta so that x squared is tan squared and I get secant squared inside of the brackets. So let's give a trig sub a try here and see if that works. Okay, if x is equal to tan theta, then the derivative dx by d theta is secant squared theta, so dx can get replaced by secant theta d theta. Okay, so let's go ahead and make that substitution. We have 1 over tan squared plus 1 is secant squared, so we get secant squared theta squared. And dx is secant. Oh, okay, I see. So because dx also has 2 copies of secant, a couple of these copies are going to disappear. And we should be able to use cosine reduction here. Okay, so in the denominator we have secant 4. In the numerator we have secant squared. So this really just becomes 1 over secant squared d theta. Or, you know, we don't really want to use secant in the denominator if we can help it. So we're going to replace that with cosine squared. And then from here, you're going to want to just kind of quickly jump back to your cosine reduction formula. So just let me find that. So cosine reduction formula. Hopefully you guys have this somewhere in your kind of cheat sheet. So here are the reduction formulas. I'm going to utilize the cosine reduction formula with n is equal to 2. So we're going to get 1/2 cosine sine plus 1/2 integral dx. All right, so what did I say? I said 1/2 cosine theta sine theta. And is it plus, I think? I think it's a plus. Yes, plus 1/2 integral of 1. Essentially, we get n 2 minus 2, so you get cosine to the 0. So we're going to... Oh, and this is d theta. My apologies, not dx. Alrighty. So let's just simplify that integral, get our constant of integration in here. And then we are going to have to work on a backward substitution to finish this up. Okay, so here we're going to get 1/2 integral of 1 is going to give us theta. Okay? So, what do we know? We know that x is equal to tan theta. So theta is equal to arctan. That's true. I also have a right angle triangle relationship that I can abuse here a little bit too. I know that tan of this reference angle must be x over 1. And then using the Pythagorean theorem, we can solve for this other side. This other side should be the root of x squared plus 1. So our end goal here is just to try to calculate cosine of that angle and sine of that angle. And let's just kind of fill in our final answer here. Okay, plus 1/2 cosine of theta is going to be adjacent over hypotenuse. Sine of this angle is going to be x over the hypotenuse. And we know that theta is equal to arctan of x. So there we go. We're going to replace theta with tan inverse or arctan. And then, you know, if we wanted to, we could maybe just kind of simplify this just a touch. We have x, we have -2 plus 1/2, so we get negative 1.5 arctans when we combine them. And then let's kind of clean this fraction up a little bit too. We're going to get x in the numerator. We're going to get 2 times x squared plus 1 in the denominator, plus our constant of integration. So that should do the trick for this particular question. All right. So let's try to kind of muscle our way through one more question. We're going to look at the following. X cubed minus 1. And we're going to begin by factoring this as a difference of cubes, okay? So we need x minus 1. And if you need to refer to your sum and difference of cubes formulas, we have the same sign, the opposite sign. This should be an x, I believe. And then we need always positive. So we get something that looks like this. And this is an irreducible quadratic. Whenever I use the sum or difference of cubes formula, this quadratic just can't be simplified any further. So this is as fully factored as that denominator is going to get. So we're really hoping to kind of break this apart into something that looks like a over top of the linear term plus a bx plus c over top of the irreducible quadratic. Okay, so that's our goal, is to try to decompose it like this. So in green, I'm going to go ahead, I'm going to set up our partial fraction decomposition, and we're going to see what we get. All right, and then we really just have to kind of multiply by the right stuff here. So let's multiply this back-end fraction by x minus 1 over x minus 1. And the front-end fraction we're going to multiply by the irreducible quadratic in both the numerator and the denominator. And doing that, we should get something like this. We should get a times the irreducible quadratic plus bx plus c times the linear. And then we get our common denominator that we're looking for. Okay, now that we have a common denominator on either side, this implies that the numerators must be the same, and I'm going to start kind of expanding through the brackets here as well. So we get a x squared plus ax plus a. Actually, hold up. I think x equals to 1 is going to be potentially a nice thing to try here. So, well, maybe I'll still expand out this first one. That's pretty easy to see. But I'll leave this second one in factored form just in case. And then we're going to, I don't know, maybe sub x is equal to 1. And I'm choosing this x value because I noticed that if I choose x equals 1, this will cause both b and c to disappear. And then hopefully we can solve for a. I'm pretty sure a is going to be 0 here, to be honest. Oh, maybe not. Maybe not. There is an interaction here that does give us an x squared as well. So let's see. When we sub in x is equal to 1, we have 1 equals a plus a plus a plus 0. So we have 3a is equal to 1, so a must be a third. Yeah, my apologies. A is a third. Okay. I don't think there's any other x values that I can easily put in to make this work. So let's go ahead, let's sub a equals 1/3 into the original equation. And I'm going to go ahead and I'm going to expand out the brackets here on the right-hand side as well. So we get bx squared. We're going to get minus bx. So we're going to get negative cx, and we're going to get plus c. And let's just try to collect all of our like terms together. So we have 1/3 x squared. There's also a bx squared that we can add to that. Okay, so collecting like terms of x here. We're going to have a 1/3 x. We're going to have a minus bx and a minus cx. So that's all of the linear stuff, the power of 1s. And then we have a 1/3 plus c as the constant number. Okay, this isn't too bad. We would like this to equal 0x squared. So that forces b to be equal to negative 1/3. Okay, so there's our second bit here. So we have a is equals to 1/3, b is equal to negative 1/3. And then the last thing that we need is we need all of this to be equal to the number 1 because we have a number 1 here over on the left-hand side. So knowing that, we have 1 is equal to 1/3 plus c. So it looks like c is also going to be negative 1/3. We can use this middle bit here to double check that all of our calculations are correct. Something isn't right. Oh, it's this number here, 1/3. This should not be negative 1/3. This should be 1 minus 1/3, which is 2/3. So C should be 2/3. My apologies. So yeah, I'm using this kind of middle portion here to kind of double check that my answers are correct, right? So 1/3 x. If b is negative 1/3, I'd get plus 1/3 x. And if c was 2/3, I'd get minus 2/3 x. And that is equal to 0x, which is exactly what we want. So everything checks out okay. So those are our coefficients we're looking for. A is 1/3, b is negative 1/3, and c is 2/3. Okay, so I'm going to grab this. We're going to fill in those numbers and see what in the heck we get on the other side. Okay, so a was equal to 1/3. So we get integral 1/3. B was negative 1/3. And C is 2/3. That's gross. Okay, well, let's break this apart into, it looks like we're going to need potentially three different fractions here. Let's kind of see. So let's at least break this one up. Let's factor out this third. And that'll give us 1 over x minus 1 dx. Let's maybe also factor out a negative third here, because I don't really like having a fraction in the numerator like this. That will give us x plus 2. Okay, so I'm just going to kind of get rid of those thirds. That cleans up the first fraction enough to know that this is going to be a logarithm kind of thing. So that's good. So that first one's done. I can just use the natural logarithm to find the antiderivative over there. This one I'm a little bit more worried about. Okay, so we might have to complete the square here, which I'm not super excited about. Let's also look at what the substitution might look like. Okay, so the substitution would be like 2x plus 1. This is going to get trickier before it gets better. So if I could somehow convert this to 2x plus 1 times dx, then that would be du, and I could potentially get a substitution pushed through here. So I'm going to try to alter this a little bit to utilize that substitution. So what I want is I want to alter this and make this look like 2x. If I multiply that by 2, I probably should multiply this other thing by 2. And to balance the multiplication by 2, I'm going to divide by 2 over here. So that's going to get us closer to what we want in the numerator. And then I think we can, I think we can make this work. Okay, so that's going to make this a 1/6. And then now we have a 2x. We have a 2x plus 1. It's there. We just have an extra 3 that we have to worry about as well. So what I'm going to decide to do here is maybe just break apart these two fractions as follows. So let's see. I'll keep the 1/6, and then we're going to separate this into two different integrals. We're going to have an integral dealing with the x portion of the question, and then an integral dealing with the leftover 3 portion. Okay, so kind of breaking apart that upper integral into two bits. And the reason I do that is so that I can kind of keep going with the u sub here. And then because there's just a single number on top of this one, I might be able to kind of force this one through with an arctan kind of integration, okay? That's my thought anyway. So let's get the second one set up, or the middle one. Doing our u substitution, we are going to get 1 over u du. So that one's not terrible. Now, arctan, we need to get the form in the denominator that we want. So let's first get rid of this 3. And then we want to complete the square inside of the denominator. Now, we need this to look like x plus something squared plus 1 would be ideal. And what would that thing need to be? So what would I need to put in here to get a 1? I think that's going to be a half. Is that true? So if I have x plus a half squared, I think that would give me the 1 in return. That would give me x squared plus x plus a quarter plus the leftover 1 that was there already. Okay. So if I were to add a quarter and subtract a quarter from this, I can complete the square. That's what I'm going to do. I'm going to add a quarter in and subtract a quarter. And that's going to allow me to complete the square. In this final integral. Okay, in the middle, obviously we get a natural logarithm of u. And let's just clean up this integral over here. So complete the square, we get x plus 1/2 squared. And we're going to get 1 minus a quarter. 1 minus a quarter, I think, is 3/4. So that is completing the square in that last integral. And the reason we do this is to try to make this an arctan kind of integral. Okay, so let me just kind of clean up some brackets before we finish up that arctan integral. This is a toughie, I'm not going to lie. So u was that big messy thing, so we should get minus 1/6 ln x squared plus x plus 1. Boom. Distributing that 1/6 through here as well, we're going to get negative 3/6. There, so that deals with the brackets, and we're in a pretty good shape to finish up that last integral. Okay, I want this to be 1. Because arctan is something squared plus 1. Okay, so that means I'm going to have to factor out a 3/4 from the denominator. Okay, so simplifying this, we get a half. And what I'm going to do is I'm going to factor out 3/4 from the denominator. Okay, that's going to give me 1 plus something squared over 3/4 plus 1. Okay, so now I have the 1 that I need in order to utilize the arctan integration. I need to get this 3/4 into the brackets. Almost done. Yeah. I fed her, but didn't walk her. I think so. Make sure she gets outside and yeah. Okay. All right, so in green, I'm just going to kind of finish up this so that we can get our arctan integration going. So x plus 1/2. And I want to kind of introduce this denominator into the squared. So right now I have this in the numerator. Now maybe you can agree that if we had something like √3/2 and squared that, we would get 3/4. Okay, so hopefully you can see that if we square root 3 over 2, that's the same thing as what I have up here in black. And that's important because that allows me to get the root 3 over 2 into this original bit. So essentially now we have x plus 1/2 over root 3 over 2, all squared, and then we just want to simplify that a little bit. Now it's not going to look very pretty. I apologize, but we get 2x plus 1 over root 3, all inside of this bracket. Okay, so let's simplify some numbers here. 2 times 3/4 is 3 over 2. And then we have 1 over that. So I think this is going to come out to be 2/3. And then over here we have 1 over this awful thing squared, 2x plus 1 over root 3 squared plus 1. So now we're in a good shape to use arctan. This is a linear thing, so this is going to come out to be arctan of 2x plus 1 over root 3. But let's go through the u substitution so you can kind of see how we would utilize a u sub to get this to work. So we would actually take this whole business and say that the derivative is equal to 2 over root 3 multiplied by the differential dx, so that we can replace dx with root 3 over 2 times du. Okay, so that's kind of the end goal here, is making a u sub to get the form that we want for arctan, and then that's going to finish up this awful, awful question for us. It looked so simple, but it turned out we needed to use quite a few tools to get this to work. This is a pretty, I would say, a pretty hard question. Okay, so performing the u sub, we get u squared plus 1. dx becomes root 3 over 2 times du. So we're just going to factor that constant out, get the arctan in here, and finish this up. Okay, bringing that out, we should get, the 2's are going to cancel here, and we're going to have root 3 over 3. This is going to become arctan of u plus some constant of integration. And then we're going to come back up, we're going to input u back into this to finish up our question. Holy Hannah, that was intense. Bada boom, there it is. You can combine the logarithms if you're feeling frisky. I don't particularly care. So there it is. There is your final solution, I believe, for this particular partial fraction decomposition question. So, like I said, I will try to get a PDF copy of the previous notes up for you guys as well. And this will just give you, I think, one really hard example and one more, I think, more manageable example for your notes, just so you have something to kind of refer back to. This last question uses those techniques that we talked about on Monday, which is, we get this really gross looking integral, and we have to kind of break it up into a substitution part because it has an x in it, and an arctan part to deal with that leftover constant number. So yeah, it's a pretty, what I would say, a pretty challenging kind of integral here. Okay, have a lovely weekend, guys. Remember, you can start working away at your third assignment. And yeah, I'll see you guys on Monday.